Hello, everybody. Hey, welcome to tonight's version of the virtual night sky. It's been a couple of weeks before we've seen between times since we last saw each other. Hey, tonight we're celebrating spring. It's about the vernal equinox and what happens at springtime and what makes spring happen, and a little bit about the seasons, a little bit about some of the things going on in space. We're going to talk a little history about sort of the movement of time and the establishment of a calendar, and a funny little thing called precession that is making everything kind of move around a little bit in space. And we're going to talk a lot about sort of some of the culture to spring, and some of the things we can look forward to in the spring night sky. So this is it. Everybody remembers it was last Friday, vernal equinox, and here we are on Wednesday. We're going to kind of go over that and talk about what's going on. So my name's Rick Alling, and I am your host of Virtual Night Sky. I'm the director of the Marston Theater behind you. Typically, when we have our programs, we always have a bunch of new people. So welcome if you're new and you haven't checked in before, and welcome back if you're a follower and you've been with us for some time, and we know there are people like that as well. The way the show's going to run tonight is I'm going to spend the first probably 20-25 minutes in space, and I'm going to just get you out into the sky, into space, and we're going to see those alignments and what sort of makes the Earth and the Sun relationship make our seasons, and what's going on, and what really makes the vernal equinox happen. Then we'll have a little question and poll break right after that. And then I will introduce one of our students, Bertie, who will give us an update on the other Mars mission. So we've been hearing a lot about Perseverance. We did a program a couple of weeks ago, several weeks ago now, about Perseverance right after the landing and what it's going to do. But there is another orbiter going around Mars, and it started turning in some good data. We've got some stuff, and we wanted to show you tonight what's going on that spacecraft as well. So Bertie will help us with that. And then I'm going to finish off, not in space, but right here in your backyard. And we're going to kind of take a look at some of the springtime constellations and some things to look for in your night sky. And that's how we're going to do it tonight. So myself, then Spurty, and then back to me, and a couple of poll breaks along the way. I've got some just housekeeping things to talk about. Sometimes I always forget to do this. You can best view. You have a lot of controls yourself, and you can sort of like just do the fit to window in the upper right-hand corner of your screen, and that would kind of help. We also changed the way we do closed captioning. We're doing a live transcript now, and so if you haven't turned it off already or already adjusted it, there is a button at the bottom of your screen, and you can actually you can leave it on and watch it if you want, or you don't have to. You can actually sort of shut it off for yourselves. We do that because it captures our voice, does the transcript for us, so it's easier for us to upload these programs on YouTube after the program. So that's it. We don't allow people to chat, but we do like people to ask questions. So don't try to use the chat button. That won't work. But if you do the Q&A button, just anything strikes your fancy along the way, you have a question about what we're talking about, you have something you'd like to know about, we will take some breaks, and in the background, students are actually kind of helping to answer those questions as they go. And we'll take a couple of breaks tonight, just so we can kind of interview and see some of those questions and answer them for you live as well. We always like to, if you're a student, especially if you're a K-12 student, if you're kind of just watching this and sort of like enjoying our program as part of your kind of extracurricular school activities, we'd like to hear from you. Not your first and last name, but you could say your first name and what grade you're in, and then kind of state your question after that. And I know that my student team is kind of watching for those, because we like to see students participate in the program. So thank you for that. And that's kind of it. I'm going to introduce the people that help make this possible. So you have probably met, at least through communication, Kim Baptista. Kim is the webmaster. She kind of gets these things organized. She sends out all the communication. She keeps track of stuff, makes us come to meetings so we can rehearse, and she keeps everything kind of moving very, very smoothly. And she does an excellent job. In fact, she added music tonight. So if you like that, make a little comment in the question box, because I like the music. That sounded pretty good. Meg Hufford is also with us. She and I are staff, and she and I are outreach staff members for the School of Earth and Space Exploration. And it is Meg and I that sort of are the host and hostess for the building. So usually when we used to, before pandemic, have lots of visitors come and see us in the facility itself, it was essentially Meg and I that were hosting those things and making those happen. We'll do that again. And so we'll start kind of lightly in the fall, tiptoe into it a little bit, but we hope by right after the first of the year that we're kind of back to a full capacity visitor experience. We'll see. Everybody's watching the same data we are, so we'll see if that works out and do that. So and then there's we've had 3 students with us pretty much for the whole thing. We're coming up on our year anniversary. Alicia Hyatt has been a Marston worker for a long time. She's joining us tonight, and as is Alex Blanche. He is also a docent in our program, and they work in the background answering questions and help us keep organized. And then Spurti Kachere is actually one of those students, but tonight she has a special role. She'll be presenting for you, and you'll see her in a little bit. I'm going to screen share now, and just sort of, I'm operating 2 pieces of equipment here. I'm actually operating 3 pieces of equipment, truth be told, and so I have to. When you see me kind of look over in this direction, I'm kind of working on another screen and have something going. And so what I'm going to do is kind of fly us through space a little bit and show you a little bit about how how the Earth-Sun relationship works and what it means to springtime. So if you don't mind, I'm just going to kind of move away. I always like, when I do a program like this, you've probably heard me say this before, there's 2 things going on. There's what's happening in space, and then there is also what we get to see. What's our personal experience, what's going on here, what can we see going on, but actually also what's happening, what are the physics of the thing, what are the properties going on in space that make things happen. And so it's always kind of a good juxtaposition for things. So I'm just going to get us a bit of a view here. The screen is just reacting a little bit slowly tonight. Sometimes it sort of straightens out over time, and so we hope it does that. But I'm going to start with a solar system view. You've all seen this before. So those inner rings there are the sun and the 4 inner rocky planets, the interior part of our solar system. The blue one is the Earth. I'm going to show you the whole system for a moment, and we're just going to focus on an Earth-Sun relationship and show you how those are working. And but the main thing I wanted to point out is these planets, those 4 inner rocky planets, those 4 outer gas giants, actually sort of built themselves into this disk. They're very, very flat. The solar system and the movement of these planets operate on a very, very flat plane. The planets do break the plane every once in a while, and actually I can sort of show you that. I built for you a little solar plane. How would that be? So basically this is the equator of the sun, essentially just stretched out into space. I think I can actually make it a little bit bigger. Can I do it? Yeah, I'm going to sort of like stretch it out so it goes all the way out past those orbits. And what you're seeing here on the screen is, so then I've just kind of created the equator of the sun stretched out into space in all directions. That's kind of like this orange thing. And you can see that the orbits of the planets just kind of fall on the plane. So their travel as they're orbiting around the sun is always going to be kind of close to that center, close to that plane itself. Now it has this name, and it's a logical name if you think about it. We call this the ecliptic plane. If you think about an eclipse means that somebody or some body is getting is causing a shadow, getting between the sun and another body and causing it to eclipse. And so sun hits something, shadow goes out into space, and eclipse happens. And so that happens when objects travel on this plane. We're very familiar with lunar eclipses and solar eclipses adjusted with the moon. Yep, in fact, both of those things, the Earth, the moon, and the sun, all have to be on the ecliptic plane in order for that to work. So that's pretty easy to think about. What we don't think about often is what's going on out in space. So I'm going to light up, here's just some constellation stick lines. These are constellations of the Zodiac. You'll recognize them when they come into view here. And notice what's going on here. See the plane that I've created, the solar equator stretched out into place, the ecliptic plane. If you look in all directions, you find that the constellations of the zodiac are sort of on the same plane. Look at that. So that means that when you look at the planets and you see them in the sky, they are always traveling against a background of only 12 constellations. The zodiac is 12 constellations, goes all the way around us. Many of you just already know the constellations. You probably know how to find some of them in space. But I don't know if people necessarily think that it is sort of the plane of the solar system. If you just keep stretching it out and out and out and out into space as far as you can go, ultimately you're going to run into these constellations, the 12 that make up the zodiac. So there's many, many constellations above this plane. Up in our northern hemisphere, there's many constellations south of us in the south. But when we're talking about planets, we're talking about the Earth-Sun relationship, we're always talking about the plane of the ecliptic and the sky we get to see in the background. Okay, so that kind of makes some sense. I think that probably is a pretty good way to see it. I am going to now I'm going to take a moment and turn off the orbits of the planets, all the other ones. I'm probably just going to kind of turn off some of the planets themselves so they don't get in our way. I'm going to set up a view now that is really just about the Earth and the Sun. So this will sort of like just take a moment. I'm sizing up the Sun and the Earth so that they're a lot more viewable. I'll leave this plane in here for now. And then we're going to kind of just go fly in and kind of see what this looks like. Let me see if I can find the Earth in this scene here. There it is, kind of hiding behind the Sun there. And so I just left that sort of that fake plane in just long enough to just sort of show you there's the equator of the Sun stretching out into space, and there's the Earth traveling in its orbit. And now I'll take it away because it sort of gets in the way. As I just do this little dance, if the Earth and Sun just dozy-do around, right, I'm just going to reinforce that idea, right? From the Earth looking through the Sun, the stars of the zodiac are in the background. If you were a resident of the Sun, if that was even possible, and you were looking at the Earth, you would always see the Earth against the background of constellations we call the zodiac. I'm going backwards now a little bit. And this should be obvious if I didn't state it yet, but 12 constellations in the zodiac, 12 months of the year. And the way this sort of operates then is every single month, from the Earth's perspective, the Sun moves one zodiac sign. So tonight we're going to find, actually, I'm going to sort of adjust us. In fact, I am. I'm using March the 20th as our sort of starting point here. So this is the Earth-Sun relationship on the day of the equinox. And if I kind of spin around here a little bit, let me do this. I'm going to make the Sun smaller because, gosh, just the very size of the Sun kind of gets in the way a little bit. And then you can see sort of as I adjust and I move the Sun, if you could look at that alignment kind of going out there, you sort of see that, right? What do you suppose is going on there, right? So as we look at the Sun, the stars that would be in the background is Pisces right here. And that means at the time of the equinox, the Sun was about right here in the sky. Now, you don't see this, remember? This is sort of, this is counterintuitive, right? So the Sun is against a background of stars, but it's daytime. And so atmosphere is up there, blue skies, too much glare. You can't see the stars in the background. But it doesn't mean they're not there. And ancient people knew this. This was actually sort of known all the way in before Greek and Roman times, that these constellations sort of were flow and followed this particular alignment of the planets and the Sun and the Earth. So how would you know where the Sun is during the day? Well, you would have to interpolate. You would have to know what the Earth is looking at midnight. That's easy because you can see stars in the sky. And you know this is a full circle of 12 constellations. So if you see one at midnight behind in the nighttime, you can extrapolate that at noontime, the opposite constellation would be there. And that's how they do this. So that's kind of cool to think about. I am now, let's see, I'm going to just introduce you to this other idea. I'm going to spin around this way. I am just going to turn off those constellations for just a second. We'll have them back in a minute, though, because I sort of want to. I'm going to take that sun and just make it a little bit bigger now so we can kind of see this relationship. And then I really, really want to spend a little bit of time examining the Earth-Sun relationship and where the light is. I think you can see in this particular view that there's a light side to the Earth and a dark side to the Earth. So the Earth, the sun's shining, its light is going this way. Half of the Earth is lit and half of the Earth is dark, or nearly half. I'll explain that in a minute. And this is the orientation that will be during the two equinoxes, not only the vernal equinox now, but 6 months later in the fall. Same orientation. Essentially, that shadow line is straight up and down, goes from pole to pole. Half the Earth is lit. And what the equinox actually means is there is essentially equal day and night, and that is all over the Earth. It's a little bit off, and I'll explain that in a minute, but that's how that works. I'm going to do this really funny, fakey little thing here. I have a pole or a toothpick I'm going to stick right through the middle of the Earth. I love the toothpick because it makes it look like an olive hanging off the top of a cocktail glass. And you can see in this particular view, oops, I moved a little bit too far, that the Earth is, again, just going to look kind of fairly straight up and down according to the sun. Now what I'm going to do is I'm actually going to change time. I'm going to move forward 3 months. And I'll do that, let's say 12 seconds and see what happens. So there goes the Earth going around the sun. If I have this right, it's going to go about a quarter of the way around. So the Earth will get behind the sun from our point of view in the ensuing 3 months. And then we're going to take a look at it again. So now the date is June the 20th. And you probably know that as being the time of the solstice. And now look what's going on. If you can see that the line of light and shadow on the Earth now doesn't go from pole to pole, it actually favors, it's leaning towards the sun. And that means the light from the sun is hitting the northern hemisphere far more than the southern hemisphere. Let's do this since I have my little, I have the ability to kind of like fly in a little closer here. Let me sort of show you this is where the axis, or what we call the North Pole of the Earth, and where it would be on the Earth. And you can see that all around it is lit. So at this time of year, let me just give you some day-night here for a little bit. We'll just make that rotate a little bit. So you can see from this thing, around the North Pole is always lit. During this time of year, as the Earth spins its 24-hour day. And if we were to look at the South Pole, of course, you guys probably already figured this out, it's not lit. And so this is really what makes our seasons happen. It's the alignment of the poles of the Earth and the axis by which it spins, right, is fixed in space, but it leans by 23.5 degrees to that plane of the ecliptic. Remember our ecliptic plane? So we have to take that axis and just tilt it over by 23.5 degrees and then allow that to move around the sun. We don't leave the ecliptic plane. We travel on that particular area all the time. But as we move around, in this case, to the backside of the sun, we're tilting our northern hemisphere towards the sun. I will just do some more of that just to sort of finish that little thought off. Let me do again. I'm going to go 12 seconds and we'll move, we'll get ourselves moved around to the other side. This will be the other equinox. And you can see the shadow changing. Look at that. So if I look at the North Pole again, you can see that the pole is at or near the shadow line on the top. The pole is at or near the shadow line on the bottom. And that really sort of like creates that other thing, the September version of the equinox, the autumnal equinox, when light is equal on both sides. Okay, reason for the seasons. That's really what we're talking about here, how that works. Okay, one more thing I want to show you while I have this funny toothpick sticking through the thing. I want to show you where in space the pole is pointing. So if I do that, and then I turn on the constellation Ursa Minor over there, this is the little bear. So, and the Little Dipper. So this is the Dipper bowl. This is the handle of the Dipper going, and this, of course, is that very, very, very special star, the North Star, Polaris. And if I orient this just right, you can sort of see the tip of our pole is pointing up at Polaris. So if we move any time during our seasons, all that whole journey around the sun, as we're moving around the sun and the tilt is orienting, so southern hemisphere towards the sun, northern hemisphere towards the sun, it's not because there's a big wobble of this particular sort of axis, it's always pointing to the same space. So we have to think of it as sort of journeying around fixed to the background stars. And it's only the orientation of the Earth to the sun that changes because of the tilt. And so that's really what the magic is that's causing winter, the winter times, the summer times, and those times in between when we're on our way from winter to summer, when we're on our way from summer to winter. And that's the magic of it. And that's what happened to us the other night. Okay, I'm going to show you one more thing before we take a break, because I'm going to pull the poles away. I think I'm going to kind of size the planets back to where they're supposed to be. Did I build a button for that? Oh, I might have. I'm just going to do it manually. I'm going to make the sun the size it's supposed to be. I'm going to make the Earth the size it's supposed to be. There it goes. I'm going to go land on the Earth, and I'm going to do it at a particular time of year that is going to be pretty important to the rest of our program here. So the planets, boom, boom, boom. Earth, sun, normal. Hang on 1 second. I'm going to go to the current time. And there it is. So there's the sun in space. And so now we're actually on the Earth. We're seeing the sun. I'll do that thing again. Let me just light up those little stick lines so you just get reoriented. Remember, this is where we said the sun was going to be. When we were in space, we were sort of like, here's the Earth, there's the sun. And you can kind of follow that alignment. You can say, okay, the sun is going to be against the background of Pisces. And that's where we're going to see it now. Now, check this out. I have the ability to put on a couple of lines. The first one is a blue line. We call this the line of the ecliptic. Does that sound familiar? Remember, I introduced you before to the ecliptic plane. That's the plane of the solar system. That's the equator of the sun stretched out into place. If you take that and sort of like visualize it from Earth, that blue line is the line of the ecliptic. And you can see pretty obviously that that line of the ecliptic is moving right through those constellations of the Zodiac. Remember that? We talked about that. And so let me do this. This is kind of cool. I can't zoom in, but I can go backwards. Watch this. I'm just going to go back. Let's see. I'm going to go back a whole week and just show you where the sun was. A week before the ecliptic. Oh, there's a moon kind of moving through the scene there too. And so what's going to happen as I go back to the time of the equinox, right? That moment that the vernal equinox happened is the exact moment that the center of the Earth and the center of the sun are aligned with our equatorial plane and the elliptical plane. That's exactly it. So what you see, right, and what we notice is that I'll just move it ahead here. So what you notice, right, when you see it, like in the city of Phoenix, all of our streets are on grid lines, right? What we see is the sun rising and the sun setting right at cardinal east and west. And that means when we're driving home from work, there's that funny time of year when the sun is just exactly in our faces as we're driving through Phoenix, right? It's on its way. It's going to cross the equator, which is the green line across the screen. It's going to cross the equator, and then start climbing up and climbing up and climbing up. Let me just move forward a month, so sort of just show you what's going to happen, because we're going to talk about this at the end of the program, which you're going to see in the night sky. Oops, a little jerky, but that's all right. So you see in a month's time, it will have moved all the way from its location crossing the equator, and now it's moving out of Pisces and into the constellation of Aries, the next constellation in the line. Now, There's some history and there's some science going on here all at once, and I need to spend some time with this. Okay, first, the science. I told you that the alignment of the Earth's axis was always the same. It's oriented to space. It's always pointing at Polaris. And that's true on a lifetime scale. You know, for you and I, that's what we're going to see. You know, for the days that we live and our kids and our grandkids, that's really what's going to be going on in space. But in a bigger scale, 25,800 years, that actually the axis does pivot all the way around. It doesn't change orientation this way. It always stays at or about the 23.5 degrees, but it kind of spins around like a giant top. And what that does is it changes the location of where the ecliptical line crosses the equator. It changes the alignment in space. So the fact that we're way out here right now is actually just today. 2,000 years ago, when this whole concept of months, a calendar year that included months, the alignment of these, signs of the zodiac, when all of this stuff was established, the first part of the year was the first day of spring, the vernal equinox, and it was also the first point of Aries. I can actually simulate that for you a little bit. Watch this. I'm going to shut off the sun a little bit because it just moves wildly when I do this, but I'm going to go back to 45 BC. And look what happened. So that particular cross, right, the ecliptic coming up the blue line, the equator going right and left, the green line are still there. The equinox is still where that happens. It's at that point where the sun crosses the equator. But now it's happening true to form, as they predicted. It's happening in the first point of Aries, when the sun is moving. And let me turn it on again. Boy, you can't even see the sun right now. When the sun is moving from the south to the north, away from Pisces and into Aries. But this wobbling, the scientific name for it is precession, or precession of nodes, is actually causing that particular moment in space to move back in retrograde, backwards across the constellations of the zodiac, until it is where it is today. So 2,000 years later, we're in Pisces. 1,000 years from now, here, let me go back. 1,000 years from now, that particular cross in space, that point where the ecliptic passes the equator, will be way back in Aquarius. You guys want to see it? Sure we can, because we can do the way forward machine as we do the way back machine. So you'll see sort of then we would be in Aquarius. And have you ever heard that term, the dawning of the age of Aquarius? Have you ever wondered where that came from? This is it, right? Sometime in the future, the vernal equinox is actually going to move all the way across Pisces and then start to actually sort of like be in the constellation of Aquarius. Now, this doesn't impact your weather. So the thing that's happening to you in springtime is where that cross happens, where the ecliptic plane and the equatorial plane match. When the sun is there, that's spring. It doesn't matter, right? Millennia ago or millennia ahead of us, sort of where that is against the background of stars. It's your climate. It belongs. It's your Earth-Sun relationship, and it doesn't matter what's going on in the sky. So spring is spring. But there's another story here. This is history. You might remember that Julius Caesar created the calendar we use today. Not only took it away from a lunar calendar cycle, because that was a mess and nobody could figure it out, made an annual calendar, and took it from 10 months to 12 months, added January and February, and made January 1st the beginning of our year. In past cultures, all of this was lunar based, and this first day of spring, this particular time, was a trigger that set off everything. The beginning of the season, the renewal, all of that stuff happened at the equinox on the spring date. And the Romans were smart enough to know that there was a difference. The Earth's year is actually 365.25 days. They were smart enough to know that every 4 years, they had to kind of add an extra day, do a leap year to keep everything in line. That was only so accurate. They missed a part. because the year isn't 365.25 days, it's 365.24 days and then some. And so the difference, right, and we could do the math, but the difference is over the course of about 1600 years from Roman days through the Middle Ages, the year slipped, the calendar year slipped against the vernal equinox. So it was happening 10 days earlier. Let me show you something. I got a little screen I got to show you here. I love the Old Farmer's Almanac. Do you guys like it? I'm just going to show you how we predict Easter and how the vernal equinox plays a role. And then we'll kind of talk about why this had to get fixed. So here are 2 pages out of the almanac. I know there's a lot of material here. It's hard to read on your screens. I have actually a close-up, but I just want to show you March and April because both of them will come into play here. This is actually just sort of a little crop and a little bit bigger and a little bit clearer. And I think you could probably see this. So these are the days of March 1 through 31. These are the days of April 1 through 30. And the vernal equinox, as you know, is, let me sort of, I'm going to get a little pen going here so I can annotate if that's all right with you. Of course it is. I know it's all right with you guys. So here we are. Last Saturday, the 20th, bum, 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 there's the vernal equinox. That was the first day of spring. The thing that Pope Gregory the 13th did when they recognized that the vernal equinox was actually receding in the calendar year because of this little problem with miscounting leap years, they noticed that the vernal equinox was slipping, and that meant the calculation for Easter was slipping. And Easter, associated with the resurrection, the most important seasonal feast, the most important one in the Christian calendar for sure, was actually slipping back in time because their way to calculate it was moving because the vernal equinox was getting out of whack. And so let me just keep going here. Here's where we are right now. There's Wednesday the 24th. And then what we will do after the vernal equinox is we're going to look for the first full moon. And it turns out in this particular case, it's next Sunday. It's a full worm moon, and you guys can look forward to that full moon on Sunday. And then after that moon, we have to go to the next available Sunday, and that's going to be Monday, Tuesday, Wednesday in April. Right here on April the 4th is going to be Easter Sunday. Easter, this is the way it works. Easter is always the first Sunday after the first full moon, after the vernal equinox. And all of this was vitally important to the Catholic Church. And that's why they did the thing where they kind of figured out how wrong they were. They added 10 days. It took a century and a half for the rest of the world to sort of catch up to all this, but they added 10 days to the calendar to bring everything back. And then they instituted this thing where every 100 days, every 400 days, they would skip every 100 days they would skip leap year. Every 400 days they'd go ahead and years they'd let it go. So every 100 years skip, and every 400 years don't skip. And by making that sort of work, it smoothed things out. And now we have the calendar we do today. And by doing those crazy maneuvers that they figured out in 1582, the vernal equinox is back where it belongs. The calculations for figuring out Easter works again, and the system is fine. So there's some historical adjustments that happen around the vernal equinox. There's some astronomical adjustments that we account for when we look at the relationship between the Earth, Sun, and the background of stars in the sky. And all of that is just tied to this really, really important time of year, Easter. So that's what's happening in space. So let me just take a break right now. We're going to go to a poll. We're going to have some questions. And then in just a couple minutes, I'm going to be back, and Spruti will give you a little presentation about mirrors and the Mars orbiting spectrometer. And then we'll be back. I'll kind of show you some night sky things before we finish up the night. So thanks for your attention. Okay, guys, I'm going to unshare screen, and you can take over. Thanks, Alicia, Alex.
Thank you, Rick. Awesome. I'm going to go ahead and launch our first poll, which is how many virtual night sky presentations have you attended? So go ahead and fill out the answer to that. And with that running in the background, I'm going to go ahead and pass things off to Alex to answer our question.
Yeah, thanks, Alicia. So we have a couple questions. One of them is, I'm so sorry if I mispronounce your name, but one of them is from Youngji, and they ask, do most star systems have their own planets align on a plane? And this is a good question. So we have the planet of the ecliptic that all the planets orbit because the way our solar system formed, we had a big cloud of gas that condensed down into a disk and started spinning, and then our planets formed from that remaining gas cloud that the sun left behind. And a lot of systems actually form in a very similar way. So most of them, not all of them, I can't really say that definitively, but a lot of them actually form in a plane where if there are multiple planets, they kind of orbit on a disk within each other. That's just because of how they usually form together. And then Benicio asks, how far away can you see the sun? This is also a very good question. And you can kind of get your answer by looking up in the night sky. We have a lot of stars like our sun in the night sky, and we can see them pretty well. There's not an exact cutoff. It depends on, how good your eyesight is, how good your telescope is. So there's not an exact limit, but, a lot of stars in our night sky are like our sun. They have a similar level of size and brightness. So you can still see those, and they're light years away. So we can still see them pretty far. They're extremely bright. So both good questions. So Alicia, back to you to finish up our poll.
Thank you so much, Alex, and thank you to everyone who asked questions. And thank you to everyone who participated in our poll. So it looks like we're about a quarter in every section almost. So thank you so much to everyone, whether it's your first time attending or whether it's your 10th plus time attending. Thank you for joining us.
That's a good distribution. I like that. So this is really good. Thank you guys for helping. All right, so I think now what we wanted to do, I'm going to get Smriti on the screen, and she's going to share her screen, just kind of give us an update on the other Mars mission. Actually, I think it's a really exciting mission, and we also have some ASU fingerprints on this particular mission as well, so it's good to hear about it. Thanks, Smriti.
Right. Thanks, Rick. Let me quickly share my screen right here. Can everybody see it? Yes. I think so. I hope you do. Okay. So what is the Emirates Mars mission? It's an orbiter named Hope, which has 3 instruments on board. They're mostly cameras, each of them seeing a different wavelength of light. The infrared camera is what ASU has, it was developed by Philip Christensen of ASU. There's a camera which sees in the visible range, and there's an ultraviolet camera. So the main aim of this mission is to map Mars's atmosphere and the dynamics, so the lower atmosphere and the middle atmosphere, and its interaction with the surface temperatures. So another interesting point about this mission is its orbit, mostly because it can map the entire surface or the entire side that is visible to it without having to stitch images. So it actually maps the entire surface of Mars that it can see. That is one of the main reasons why the dynamics of the atmosphere can be observed and plotted in real time, which is a great thing. So let me just quickly explain what Emirates is. So Emirates is stands for Emirates Mars Infrared Spectrometer. Basically, this is a thermal imaging camera which sees in the infrared range. Infrared range is so infrared light mostly deals with thermal imaging. So heat is, we receive heat from the infrared radiation here on Earth. The same thing happens on Mars. So the radiation that Mars receives from the sun, since Mars also has an atmosphere, a lot of it can be absorbed or reflected. So infrared spectrometer helps us see the surface and the temperature on the surface and its interaction with the atmosphere. At ASU, Philip Christensen, a faculty at the School of Earth and Space Exploration, helped them develop the camera. And we have a contribution in the various other, along with the various other cameras that EMM has. So here is the data that we started receiving. This data is very fresh. We received it on February 20th, 2021. So not long ago. And EMIRS maps the nighttime surface temperature and its atmospheric reaction, not reaction, let's say atmospheric interaction. So as you can see, the top part of the image shows surface temperature. There's a small blue patch on the surface. It's the Arabian Terra, which is a patch on the Martian surface with a lot of craters and a lot of geological variation. It shows that it's way cooler than all the other patches or the rest of the surface. This is a nighttime image, so you can see things are a little cooler. To your right hand side, you'll see a little warm patch. That is the part where that's the part of Martian dawn. So it's redder because it's receiving a lot of radiation from the sun. That blue patch, however, reveals that that particular surface or that particular feature on Mars has a very low thermal inertia. So thermal inertia essentially means its capacity to hold heat is low. So it changes temperatures very quickly with its environment. So this is something which was found or revealed by emirs, along with a lot of important data that we are finding out about the Martian surface and the lower atmosphere. So lower atmosphere is about 25 kilometers from the surface. So as you can, the lower graph or the lower image is is the atmospheric temperature, and you can see that it is way more uniform than the surface. So it tells a lot about the composition of the Martian atmosphere and the way it is distributed. So this data is going to be very useful for the entire world when it comes to mapping the surface and the geodynamics of the Martian surface. So since it's advantageous for the mission, to conduct such say global images or global maps throughout its lifetime, it's going to help us reveal a lot more about the surface and what terrain on Mars shows what kind of temperatures during the day or during the night. So these kind of data points is the main objective of this mission. And we at ASU are very proud that one of our faculty members has developed or has contributed hugely to this mission. So this was a little bit about emirs, and we hope to collect more information, and maybe we can share some more with you when we find out more about it. So this is pretty much about it. We hope to get more information, and if you want more information about the mission, you can find the link in the chat. It'll take you to the webpage of the EMM or the Emirates Mars mission, and you can find out all about the mission. So back to you, Rick.
Thank you, Smriti. That's absolutely excellent. I think one of the things that I've seen many interviews with Phil Christensen and the work that they do, and they're taking images, but it's not like a camera image. They're not taking imagery which you can look at and sort of see it. They're taking imagery that is giving them values of infrared energy. And so Phil calls it squiggly line science. And essentially what they do is they fly around and they just take graphs. They get these graphs of information that is energy coming in wavelengths of infrared. And they can pinpoint in many of those things the type of material that is on the surface because they have signatures. So not only are they measuring for the whole temperature of the surface, the temperature of the atmosphere, but they're also can see enough detail with enough resolution to tell some of the stuff that's going on the surface that's causing it to be cooler or warmer. And so that's pretty exciting. And so it was really kind of nice to see about a week or so ago some of these first images come down, some of the first reports happening, and we wanted to get in front of you. We will be over the course of the next several weeks, just following these projects, make sure that you know the latest on Perseverance, and I'll make some announcements about that kind of towards the end of the program. So we will always try to do some sort of combination of something that's topical and about the time of year. We'll just do a night sky presentation in most presentations when we can get to that, and we'll also keep you on track about some of these missions and whatnot. Spruti, you did an excellent job. Thank you for that. Okay, I'm going to share screen again. This is a different program. This is the one, it's a little planetarium style program. It takes me just a second to launch here. It's always a little chunky. I actually use a iPad for this, and the program is called Sky Safari. And this one's called Sky Safari Pro, which means it costs just a little bit, but it's still not that much. And so you might want to do this with your screen as well. What I do is I just sort of, I'm going to start with this particular image, and then we'll move around the sky a little bit as we can. Let me see if I can get this mostly full in here. I'm going to twist it this way. Sorry about that. Just so you can see a little bit more of what's going on. What's happening here is everything within that green circle is in your sky right now. So the circle is your horizon. Everything that is sort of that translucent green color around is below the horizon. You can't see it. And but everything in the sky is there. And I'm going to kind of just walk you around. I'm going to kind of show you some things, 3 different areas of the sky, and give you some things to look for. So as we go along, I think, as most of you know, if you remember the program from a couple of weeks ago, and then a couple of weeks before that, this is just an exciting time of year to look at the night sky, because there is a lot of bright stars, a lot of bright constellations. This central area, kind of centered on the lower part of my circle right now, is still up. And so this is the constellations like Orion, and it's beautiful. Betelgeuse and Rigel is there. The brightest star in the sky, Sirius, the dog star, is still up. And so there's still time. They're starting to move towards the western horizon. They're starting to get into a position where we're going to lose them into the glare of the sun in the next month or so. But right now, kind of go out and keep taking a look. I am going to orient ourselves just right towards the west to start with. And I'm going to do a couple of different takes here. So let me just show you this first, because I want you to look for a couple of things right here. And what I do is I take a little screenshot so that I can draw on the screen as we kind of go forward. There it is. So this is looking directly towards the west. And the key here is to find the head of Taurus. This is Taurus, the bull. That's one of those signs of the zodiac, right? And there's a V shape in the sky. And on one side of it, towards your left right here, is a really bright orange star, and it's called Aldebaran. And so that's easy to find. Find the V, a bright orange star on the left is Aldebaran. You know you're there, and you found the face of the bull. I don't know how people see this different ways, but let me sort of just give you a little bowl face. And then these stars up here sort of represent, if you want, the direction or the point of his horns as they go up. The one on the right is called El Nath. And that's a very, very important star, easy to find. It's the brightest one of the points of the bowl. And then the other one over here is the other point of the bowl. A couple of cool things are going on here. One is, if you've ever seen images of that famous Crab Nebula, the supernova explosion remnant and all that stuff, you can't see it with the naked eye. It takes a really nice telescope to do it, but it actually sort of happens to be kind of right here in between those 2 stars, the horns of the bowl in this particular part of space. So just sort of like, you can kind of like find where it is and all of that. The other thing going on here is this is the planet Mars. And so 2 weeks ago, I had Mars right here on the screen. Let me see if I can sort of like zoom in just a little bit. And right down here is the Pleiades, the 7 sisters. And so Mars has come through in this particular direction. It passed right by the Pleiades. 2 weeks ago when we had our program, I showed you Mars right there. Boom, boom, boom. And this gives you a really good sense of how far it moves in 2 weeks. There it is. It's heading in this direction, and it's going to go right through the goalposts. It's going to go right by the Crab Nebula, so it'll be kind of fun to see if people capture that particular information, and head out up between the horns of the bowl and off into space, or off into so we'll track it as it goes. We're going to do a program in about 6 weeks, just kind of about stars again, May 5th, in fact, Cinco de Mayo. It's going to be, about planets in the inner solar system, because Mercury, Venus, Mars will all be up, and they'll all be sort of like ready for us to take a look at. So that's a good thing to look for, okay? The other thing I want to show you in this particular part of the sky, let's see if you can trace this out. Oh, this really, really bright star is one of the brighter stars in the sky. It's called Capella. And so now you see the orientation. There's the Pleiades. You see the head of the bowl, horns, those points of the horns, and this really bright star up here. And I'll just sort of trace out. Capella is the brightest star of a constellation called Aries. Aries is known as the charioteer. And you can sort of loosely take this sort of like polygon kind of shape there and encompass the entire constellation of Aries. Two interesting things, and one I'm going to send you out to go look for. One is that Elnath, remember that? It's actually one of those stars that doesn't happen very often that shares two constellations. So they actually meet. So people kind of talk about it as being the end of the horn of the bull, and it's also attached to Aries and the shape of its particular constellation. So it just sort of like trades. There's a couple of that do that. Andromeda's head is like that, if you remember. The other thing I wanted to show you is right here next to Capella. Capella is known as the goat star. And right here, I've showed you this before, but I'm going to do it again because I want you to see this. There's this little tiny triangle, little isosceles triangle of stars right there. Those are baby goats. So if Capella is the goat star, these three little stars are called the kids. I don't know if you know that, but baby goats have a name, and we call those kids. And so it's a really good thing to take your kids out into the backyard or out into the front yard and find those stars, find that tiny little triangle. It's a little bit hard to see, but you can do it. You can see it from Phoenix if you work really hard at it, and that'll be important. Okay, another part of the sky. I wasn't going to show you this, but now I am in the north part of the sky. So now I'm facing exactly north. I'll kind of like show you a little bit more about what the sky looks like right here. But I just remembered an answer to a, sorry. Hang on. It looks like I have to relaunch. Sorry about that. This is called fumble fingers. There it is. And it's just having trouble catching up. Okay. So now I'm looking straight north, and I'm going to do a little screenshot so I can kind of scope some things out here. You'll see here is the Big Dipper, very famous Big Dipper. That's easy to see. And so that's going to be just a little bit over towards the east as you're looking north, and a little bit over towards the west when you're looking up is this W shape, Cassiopeia. The reason, and then of course everybody knows this is that pole star. We've talked about it a lot in the other part of the program where the axis of the Earth points to this particular part of the sky right here. But let me show you Cassiopeia for a second. Cassiopeia is made up of 5 bright stars that make up the W or the M as you want to, but I want to show you this one right here. And do you remember from our first question break, the young lady said, what does our star look like from distance? What does the sun look like from a distance? This particular star right there is the same brightness and the same size as your sun, as your star. And it's 20 light years away. So it took light from that star 20 years to get here. You're seeing it 20 years in the past, but you're also, if you can find that particular star in the sky, you're seeing what our sun would look like if we were 20 light years away. If we were off visiting this star in the constellation Cassiopeia and turning around and looking back the other direction, that little star, something like that, would be exactly what our sun looks like. So that's kind of fun to think about, and it's another fun thing to find. Let me just show you one more time. Here's the shape of the M or the W, the 5 bright stars that make that up. It's not one of those. It's a 6th star, kind of in between these 2 bright ones right there, and it's called Mu Cassiopeia, and it should be kind of fun to see. Okay, last thing is back in the west, and I want to show you some constellations of the Zodiac and some stuff to follow over the course of the next next couple of days and weeks. I'm going to try to do a screenshot again. So now you're looking back west. Remember, we already talked a little bit about the head of the bowl and Mars and its travel through space, but I want to show you just a little bit more. Right here is Gemini the Twins. And that's a constellation of the Zodiac, right? This is Taurus the bull. We talked a lot about it. And here's its horns sticking out and all that kind of stuff. And so that's a constellation of the Zodiac. And going backwards, this one right here is Aries. And remember, Aries used to be the first point of spring, but now because of precession, remember, right? So now the sun isn't moving into Aries at the first point of spring. It's actually well into Pisces in the first day of spring. And so indeed, I can kind of show you what that will look like. Let me get rid of, I'm going to just have to do another screenshot real quick. I didn't make myself high enough. Okay, so here's Taurus again, here's Aries again, and then remember where we saw this situated in the sky? Remember the sun was kind of like right in here, and there was a little arm of Pisces that came up over this way, and another arm of Pisces that kind of came up over in this particular way. And these become the fishes, this little lobe over here and this little lobe over here. Those are the fishes of Pisces, and that's where the sun is. So if you were following along, and this all ties together, right? Many, many years, 2,000 years ago, if we were out looking at the night sky tonight back then, right, just after the springtime, we wouldn't be able to see Aries. It would already be buried in the sunlight. And we would be able to see Mars and the twins, Gemini, kind of following it down. So try to do this over the next couple of months. It's really beautiful star watching weather. Watch as the sun, just one at a time, starts to swallow these constellations. So Pisces is now kind of rendered invisible because it's lost in the sunset. Aries will follow very, very quickly. A month from now, we'll have a program. We won't be able to see it anymore because the sun will be in its way. And then a month later, Taurus will drop down. And then a month after that, Gemini is going to meet the horizon and start fading into the sunlight. And so you can start to follow these. There are always 6 constellations of the Zodiac in the sky at any given time, right? And every month, one of them drops off and one of them is added to the other side, rises in the east. And that's a really good way to just follow the whole cycle of the whole year. And since you saw what was going on in space, you understand the juxtaposition between where the sun is and where Pisces is, and the importance of where that is in relation to the vernal equinox. So that's really what I wanted to talk about tonight as far as in the sky and some things to look for. I'm going to just really quickly just sort of like turn it back over to students. Let's do one more poll, and then I'll give you some things to think about for the next couple of weeks, and then we'll be off and running. Thank you. Oops, I guess you want me to stop sharing, don't you?
All right. I don't know if Alex wants to go ahead and start our pull off.
Yes, one second.
Or I can. Awesome.
I can do it.
Great, thanks.
Okay. So here's a poll. What is the line that the sun moves along the sky that defines the constellation of the Zodiac? And while you guys answer that, I'll let Alicia take a poll question.
Thank you. Awesome. So I'm going to answer 2 questions kind of at once. So Vivon, sorry if I pronounced that wrong, but Vivon asked, which is the closest black hole to Earth? And then another question that we had was by Robin, and it is, what is at the center of the galaxy? So both of those answers are kind of Sagittarius A. And so the best way to explain this is if you look at the constellation Sagittarius, and if you were to look 26,000 light years into Sagittarius, you would actually be looking at the center of our galaxy, and you would be looking at a supermassive black hole in the center of our galaxy. And so it's named Sagittarius A. And you would also, I know if you were to look at an image of the Milky Way galaxy, right, you're going to see a really shiny object in the center of it. And that's not the supermassive black hole, obviously. But what that is it's where hot, massive stars like to clump together. And so it does look like there's a lot of light coming out of that area. But don't be fooled, there is a supermassive black hole in the center of our galaxy. So I hope that answers your question. And then back to Alex with the poll update.
All right, thank you. So a lot of you got the right answer, spot on. You guys, the majority of you said line of the ecliptic, and that's exactly right. Great.
Hey, we did some good work tonight then. That's great. Super cool. All right. All right, everybody. So in 2 weeks, we're going to meet again, and we're going to kind of just concentrate on, it's another program that gets a lot into how the sky works. It's the way we started about a year ago. Many people won't remember that. Many people have joined us and become our friends since then. So yeah, sort of like we were talking today, that sort of relationship of the planets and the ecliptic and kind of some detail about that. We're going to do things like that, but in this particular case, it's going to be about how we see all of the stars and how these constellations move. Why do they behave like they do, and how does that relate to seasons and some stories along the way? So that's, we're going to engage that. And we will have other visits and other updates along the way. 4 weeks from now, I'm kind of excited about this because we're doing a geology program. We're going to have a guest, Dr. Stephen Simkin. He's a geologist at the School of Earth and Space Exploration. And the reason for this is the day after our event is Earth Day. And so because our school is Earth and Space, we thought it's about time we start seeing geology. Steve is going to talk about the geology of Arizona in particular, and that's kind of cool. So we'll have stuff to look for again. And I'm also going to ask him some questions about the Phoenix Basin and our area. And when we look up at the mountains in the preserve and Camelback and South Mountain, what are we exactly seeing? And so in keeping with this idea, things that we get to see and things that we get to learn about in science, that's how we're going to approach that in a month. So I'm very excited about that. We also have another thing coming on, the New Discoveries lecture series. And so what we have been doing in practice in the Marston Theater, which is behind me, it's empty, it's closed for the pandemic. But we have had this tradition of doing what we call New Discoveries lecture series. And these are professors and researchers, and they do about a 45 to 50-minute presentation. And then there's a really good, serious question and answer afterwards, and they're delving really, really deep into their scientific research, and they're really fascinating to watch. There is a range of experiences that we're going to do. In this particular case, it'll be desert ecosystems, and so we have two professors on tap, and they will both be handling the lecture specifically about deserts and desert ecosystems and desertification of landscape, and so I think that'll be really, really a great program. That is actually on April the 22nd. And so that's not one of our programs. That's actually another thing. It will be the day after, it actually is on Earth Day. So it'll be the day after our April 21st virtual night sky on Wednesday. That Thursday, the very next evening, is this. And so we'll announce it again as we get going. So thank you very, very much. What you're going to look forward to is a survey will come out. Kim will send that within the next day or two. We do that all the time, and that's a really good chance for you to say, you know, what you liked and what you didn't like, what you want to see, any comments you might have about what we might program in the future. We take those very seriously, and I think that will be a really, really great thing for you to do if you take the time to do that. So I would know we've run over by a couple of minutes. That's pretty traditional these days, and so I'm going to take this opportunity. I'm going to first ask my team if I forgot to say anything, but while they're reacting to that, I'm going to say goodbye. Welcome to spring. You saw what's happening in space. It's a very, very specific thing that happens between the alignment of the Earth and the sun. But what actually we get to observe is the grass is getting greener. We have lovebirds that are just descending on one of our trees because it's budding right now. The days are getting a little bit warmer, and this is really what's going on. There's an astronomical phenomenon and a physics of our relationship with the sun that's making it happen. What we get to enjoy is the fresh flowers and the blooms and all the things that go with that. So welcome to spring. I'm glad you joined us tonight, and we'll see you in about 2 weeks. Thank you, guys. Thank you.